Hey everyone, it's Leon. How you doing? Today I want to show you guys how to create some really cool animated visualizations, but not just any old kind of animated visualizations in our studio, but specifically with principal component analysis. And to do that, we're going to go ahead and use the iris flower dataset for this endeavor. Now, the iris flower dataset is a multivariate dataset, which was introduced by a British statistician, biologist by the name of Ronald Fisher in the 1930s. And so what he did was made use of multiple measurements in taxonomic problems. And so sometimes we call this the Anderson iris dataset because a gentleman by the name of Edgar Anderson collected the data to quantify the morphologic variation of iris flowers of 3 related species. And so the reason we're using this data set is really because it's become a typical test case for so many different statistical classification techniques, including but not limited to support vector machines. But today, what we'll do is leverage principal component analysis as a dimensionality reduction technique and visualize it with an animation using the gganimate package. But before we can do all that, let's go ahead and ensure that we've installed or have installed the requisite packages and or libraries. So the first one will be, and I'm going to go ahead and comment this out because I already have this installed. The first one will be the DevTools package. So we want to install that packages DevTools like so. And once we've done that, what we want to do is load this DevTools package as a library as such. And after we've brought this DevTools library in, we'll go ahead and install it from GitHub using the following repo, Gasambara /facto extra. So what we're doing is installing the facto extra package using the development tools library from GitHub. Of course, when you're doing this, what you want to ensure to do is to uncomment these lines and actually run it through your RStudio. Okay, so once we've done that, the first thing we'll do now is bring in the facto extra package that we've just installed as a library. And because we're going to be animating this, we might as well just bring in gganimate. But one very important step that we forgot is if we don't have gganimate, we need to install it. So in a similar manner, install.packages in quotation marks gganimate. So I'll leave this here for your reference so that you can circle back and follow the steps. And of course, if you need to install any of these packages from lines 1 to 4, make sure you do so by uncommenting these lines and running them through the code window or the console window at the bottom. Okay, so once we brought in the libraries, we're going to go ahead and examine the iris flower data set, which is already in RStudio. We're going to go ahead and run all this. And as we can see on the right-hand side in the global environment, we have our iris flower data set, which contains 150 observations and 5 variables. And now it's evident in our console window at the bottom. Of course, we can also inspect it in the following manner. Here, run that, and the first 6 observations give us data for the Setosa species. So, as mentioned in the very beginning, what we're going to do is apply a specific use case to this data set, and that is principal component analysis. So, principal component analysis is a dimensionality reduction technique for large data sets, what it does is really increase the interpretability, but at the same time, minimizes any kind of potential information loss. So without any further ado, let's create a variable for our principal component analysis, or PCA. We'll call it res.pca. I know some of you wanted to say res.pct, but this is res.pca. And we're going to go ahead and assign it to prcomp, which is short for principal components. And it takes in the following arguments. Our first one will be iris, which is our data set. And we can't just say iris, the entire data set, right? Because we're looking for numerical features, and those are contained in the first 4 columns. So by negating the 5th column, we ensure that we have our numerical features as follows: iris, bracket, comma, -5, close bracket. And it's important in PCA to normalize the data, so we're going to go ahead and scale it as follows. Scale equals true, and there you go. You got your PCA variable assigned. And in PCA, what we want to do is determine how much variability is explained in the data set by different principal components. So to do that, we'll create a new variable for the explanation of variability and call it something like var underscore explained. And this takes in our PCA variable, which which we put the standard deviation and square it on. Divide that by the sum of the same function and square it again. Okay, let's go ahead and round it to 4 decimal places. So to do that, we're going to go ahead and put round in the front of this function, close parentheses here, multiply this by 100 because it's going to be decimals. So we want to do that with 100% and round it to 4 decimal places. And so what this function does is show how much variability is explained. So in this process of dimensionality reduction, the determination of new variables or the principal components, what's taking place is there's a reduction to solve an eigenvalue or eigenvector problem. And so that's what this function does. So on the next line, what we want to do is finally create our visualization to visualize these eigenvalues. And the purpose of installing the facto extra package was to give us this fviz underscore eig for eigenvalues or eigenvalues, however you pronounce it. And this function takes in the following arguments: our principal component function, res.pca. And from here, we can go ahead and run it, and we have our visualization over on the right-hand side. And this is what we call a Scree plot. And so right now there are 4 dimensions. Remember, we removed the 5th one, the 5th column. And in the first dimension, the first principal component, we have, see right now it's a little bit difficult to see exactly how much percentage of explained variance exists, but it's over 60. And in the second dimension, we have even way less, 20, and it gets reduced even further at each dimension as it progresses. But let's say we actually wanted to see the exact percentage of this diminishing variability. So what we can do is go back to our res.pca in the fviz function. And if I recall correctly, what we can do here is give it a add labels. Exactly, that's the one. and say true. So now, when we run this again, we can see our exact percentages for each respective dimension. Okay, so that's pretty cool. But let's say, what if now we're not satisfied with just the static Scree plot? Let's say we want to visualize it and by animating it, right? So what we can do from here is, now that we've loaded our gganimate library in line 7 of the code, we can leverage it. So let's go ahead and assign this function on line 14 to a new variable. Let's just call it fviz for visualization. And from here, we're going to, simple as this, animate it. So animated fviz plus, so this is where we're using, this is where it gets a little bit tricky, but if you can follow the steps, I promise you that this is reproducible in subsequent iterations of models that involve PCA, especially when you're using similar kind of variable assignment logic. So this function will take in the fviz, the visualization, plus, now what do animations have? They have different kinds of transitions, right? Especially if you're accustomed to doing animations in PowerPoint, you're familiar with transitions. So in a similar fashion, this gganimate library is rich with various kinds of transitions. So the transition that we're going to use for this specific use case, PCA, is the transition called reveal. So it's transition underscore reveal, and it takes in our, what do we want to see? We want to look at this variability that's explained, so we're going to bring in var explained. Okay, and when we run it as is, nothing is going to happen yet, because while we've assigned this to an animated function, what's left to do is the final step, and that is to actually animate it. And that's what this gganimate package does, is it animates it, if you can see from the second item in this pseudo dropdown. So this animate function will animate our animated variable, and sometimes you can specify the renderer. You don't necessarily have to, but I prefer to always. So I always go with a renderer equals gifsky or gifsky, however you pronounce it, renderer. That's an empty function. And right now it looks a little clunky and a little messy. You'll see in a minute. So what's going to be really cool in just a sec is when we run all of this like so. First of all, we have a little bit of a hiccup right now. We have an error, so we have to kind of determine what this error is and where it's originating from and how we're going to troubleshoot it. But I promise you, it's nothing that can't be fixed in just a few short tweaks and manipulations. So let's see what's going on. We have an error in sequence default range length out number frames from must be a finite number. Oh, okay. So for those actual eigenvalues, and we missed a step between variance explained or variability explained and fviz, and that would be to actually get those eigenvalues. So to get those eigenvalues, we use get eig or get eig. I'm always tossed between how to pronounce these. And that's from our PCA, principal components. So let's go ahead and run that again. Okay, and so there's still a little bit of an error. And in this case, Iris, let's see if this is the difference, if we need to take out the, no, that's not it. Scale equals true, variance explained, round, RESPCA standard deviation squared sum. Oh, okay. So we forgot an extra parentheses here. I think that should do it. So when running this, you want to ensure that you have the correct number of parentheses. And so whenever you have a animation, what it does is it renders it at the bottom, and you can see it actually taking shape. So on the right-hand side, we have this funny-looking animation. Right now, it doesn't look like much of anything. We can't really see it in its entirety. So what we can do is, first things first, in the animate function on line 17, we can specify the height parameter. Let's say 350, and you can adjust these on an as-needed basis. And the resolution, which will be, let's say, 100% or 100. Let's go ahead and run that again and see what this looks like. So it's rendering at 10 frames per second, now 11. Got about 2 seconds up. It's going fast. And let's see what this comes out to as a GIF. Cool. So now we can kind of see it moving. But let's say we don't want to see it moving from the right to the left. Let's say we want to actually see it moving from the first principal component. Sorry for the little twitching there on the screen. From the first principal component over down to the fourth principal component, or the fourth dimension. So what we can do is specify this as a sequence along the variability explained. So to do that, we'll go back to line 16 where we use the animated function, and in the transition revealed, we'll go ahead and specify sequence along, or SEQ underscore along variability explained, like so. Let's go. Oh, we forgot one parentheses. Let's go ahead and run that again and see if it changed the order or direction of this animation. Awesome. And surely enough, we have our movement or animation going from the first principal component down to the last. So as this, okay, so that's cool. And so now we can do something a little bit fancier if we'd like. And let's say we want to increase the width of this line, right? That connects to each bar. So to do that, remember, gganimate is really an extension of ggplot 2. And fviz underscore eeg or eig is sort of like a ggplot type of visualization. It's not stated explicitly, but it can use ggplot parameters. So let's go ahead and another cool thing we can do is set this to a GG classic theme by going with GG theme equals theme underscore classic. And that's an empty function. And let's go ahead and say, yeah, let's go ahead and run that. So what's going to happen is we're going to get rid of all of those squares or axes, grids on the right-hand side. Nice. And let's actually increase the line thickness by specifying the geometric line parameter, geom underscore line. Let's give it a size of 1 and color it blue. So not only will the line thickness change, but so will the color. Let's test that. Okay, it's rendering a little faster. Actually, no, it's taking about the same amount of time. And, oh, there it goes. Okay, cool. So now we've changed the size and color of the line. So there's a lot of cool little applications with this gganimate library. One of those I thought I'd share with you today is this Scree Plot animation using principal component analysis with the iris dataset. All right, well, thanks for tuning in. Bye now.